Great. As stated, my name is Hugh Herr. I co-direct the Center for Leg Prostheses. I'll divide my talk into 3 areas. I'm convinced we can make rapid progress. One area is body imaging. How can we image the body with conventional as well as novel tools. Second is soft tissue modeling, tissue biomechanics, and thirdly, functional CAD/CAM, computer-aided design, and computer-aided manufacturing. So our goal is to seek a quantitative while simultaneously decreasing cost. Today, a transtibial socket in the US reimburses for around $8,000 to $10,000 US, and it takes often a month to build through an iterative artisanal process of building several check sockets and going through an empirical optimization. And often, after that month of experimentation, the interface still is painful and does not work. So can we actually use real scientific tools and real mathematics and science to solve this problem? So we threw standard imaging technologies at the problem. This is just an MRI image of a transtibial limb. You see the femur, fibula, tibia, and the patella bone. And we built novel robotic machines. This is a crazy 14 actuator system that comes in and finds the surface of the body and applies position and speed disturbances while measuring force. So from these data, one can model the residuum. We use a second-order Ogden formulation. The red curve is experimental data from a very precise robot, and the green is the simulation. So such a model tells you when you push on the residual limb and apply a delta X and a delta V, what forces can one expect? So why build a digital representation of the body part for which interface is sought? Well, in the simulation world, you can optimize. You can iterate over thousands and thousands of socket designs and really explore fundamentally what is fit and actually have a scientific approach to the problem. So I'm going to run a simulation on the left. What you see is dawning of the synthetic skin or the socket, and then load bearing in an optimization sequence. So it's dawning, and then you see load bearing. So what we do, in fact, is we iterate over equilibria shape of the interface, as well as the mechanical impedance of the interface at each anatomical point. We can then use digital fabrication to 3D print the interface and then evaluate it experimentally. So we are building interfaces without any human decisions, any hands-on artisanal practice, and we're already seeing very large reductions in peak pressures in a walking gait cycle around bony protuberances. I can say that I'll never use a prosthetic socket for the rest of my life that's not derived via mathematics, which is very fun. MRIs are very expensive. The robotic device that you saw is very expensive and bulky with a large footprint. Can we think of novel tools that are inexpensive with small footprints and highly portable to get the imaging and palpation data? So we're designing a glove rich in sensors and actuators. And essentially, by moving the hand around the residuum and massaging the residuum, we'll get sufficient data to build the biomechanical model and also the model of the interface. So what does that world look like? You get the data in a few minutes. You send it to fast computers. You have a design in, 30 minutes. And then you 3D print in several hours. So instead of a month, let's build interfaces in a day. And let's have it cost $300, not $10,000. Moving on to dynamic interface. Clearly, if we want to build mechatronic parts that have the same mass, volume, and dynamics as the biological counterpart, we have to know something about how the human works So my lab, and of course many labs around the world, look at what's happening in standing and walking and running in humans. So we model gait, and then we use such models to inform both mechanical and software design of prosthetic devices. So I'm going to tell you about one model that we've been looking at for some time. It's called the Endo-Her model. There's 3 models shown here: Endo-Her, Guile-Her, and Anderson and Pandy. So the space is, on the y-axis is the cross-correlation coefficient R. So if a model walks perfectly like a human in a kinematic sense, you have an R equal 1. On the x-axis is the metabolic cost to transport a dimensionless quantity, the amount of energy to transport unit weight, unit distance. So, and the shaded region is where a human walks metabolically. So we want a model that's within the shaded region and with an R value that's high. So in this model, we have a simplified abstraction of muscle tendons, specifically muscle tendons that span the knee joint and dorsiflex the ankle. This is only for preferred walking speeds on a flat level surface. So the simplification is under neural control, the muscle tendon behaves like a spring. So you apply a neural command, there's a spring-like force. When you release the neural command, there's no force. So we apply that to all the muscles that span the knee and that dorsiflex the ankle. If you do a clamped optimization, where you have the hip, knee, and ankle move via kinematic data measured from a human, and various stiffnesses and isometric force generation times, you can in fact at the knee track very well what a human knee does in torque across the gait cycle. For dynamically, we have to apply reflex models to the muscles, hill-type muscles being modeled in the limb. They are the soleus muscle, monoarticular muscle of the ankle, and 2 monoarticular hip flexor extensors. So in the field, it's been observed or hypothesized that the dominant feedback loop of the soleus muscle is a force feedback. There's position and speed feedback as well, but force is dominant when the foot is in contact with the ground. So we apply that in the model. For the monoarticular hip muscles, we do essentially a PD control to keep the body upright in pitch. We then run an for dynamic optimization. We vary morphology and control parameters, and we find the solution that falls within the metabolic cost of transport that kinematically walks like a human to the greatest extent. So such a model informs what we build. I'm the founder of a company called Bionics, and we recently launched this new powered ankle. It has an integrated battery in the front there that snaps in, and now has a battery runtime at least of 1 day. So I'm going to tell you now how this device works and how it's informed by the model. Mechatronically, we have a series elastic actuator. You can think of this as a muscle in series with a tendon. And then in parallel to that is a unidirectional spring. Unidirectional means that this parallel spring is only engaged in dorsiflexion, but in plantar flexion it is not engaged. So powered plantar flexion and controlled plantar flexion are not impeded by the physical spring. Essentially, in the upper plot, we see the torque angle curve in walking, in level ground walking. And by subtracting away the parallel spring, you get the torque requirement of the series elastic actuator. So the presence of the parallelisticity and the series elasticity increases the instantaneous output power of the device. And by tuning both parallel and series springs, we can not only amplify mechanical power output, but also minimize the energy required from the battery. So this device is a monoarticular design. It captures the bottom of the model. There is no artificial calf muscle represented in this design. I'll talk about that in a few few slides. So control system, we basically have an internal biophysical representation of the missing leg that we input joint state, measure joint state, and the model tells us the desired torque, and then we have a robotic feedback control system that tracks that torque. The neuromuscular model is shown here. We use a hill-type muscle model with a nonlinear tendon. Again, we measure position and speed of the robotic joint, and then we estimate the length and speed of the muscle-tendon complex, a virtual muscle tendon. And then we also model a reflex loop. Again, for example, the calf muscle, we have evidence from the model that the dominant reflex is a force feedback when the foot's in contact with the ground, meaning the higher the force borne by the virtual muscle, the greater is the activation of that muscle. And then there's a robotic controller that tracks that torque. So we've discovered that by attempting to represent the biophysics in the controller, one gets very friendly emergent behavior. With this force feedback, it's a very simple control law with the properties that the faster, I'm wearing two of these robots, the faster I walk, the greater is the power output. And if I walk fast, you can hear me more because the transmission is spinning. And I can run, and it responds with very little delay. If I walk uphill, I get even more power and work. When I walk downhill, the loop goes in the opposite direction, and the device breaks my movement. That's really cool because the robot knows nothing about its environment. It doesn't know how fast I'm moving, doesn't know that I'm walking on a wooded floor. If I walked up and down hills, it wouldn't know the hill was there. So by following the biophysics, you get a situation where the robot need not sense everything about the world. In fact, it only has to sense very, very few things. From this design, we get normalized mechanics. On the bottom, you see the network of the ankle joint increasing with increasing walking speed. That's the shaded region. In the upper plot, you see the toe-off angle matches a biological limb well. It's hard to see the shaded region. These normalized mechanics result in normalized preferred walking speed compared to persons with biological limbs, as well as normalized metabolic cost of transport. So this is a walking velocity versus metabolic cost of transport that I defined earlier. The blue data are a person with a bionic limb. The red are the same persons with transtibial amputation wearing high-profile carbon devices, and the green is an age-weight, height-matched person with biological limbs. So this means if you have a box and all you can measure from a human in the box is their preferred speed and metabolism, you can't tell statistically whether they have a bionic limb or a perfectly natural biological one, which is fun. I think the dominant legacy of robotics used in the realm of prostheses will be, once these devices are pervasive into society, will be the reduction in musculoskeletal stress. First, let me tell you a story related to walking and knee stress. So in the trailing leg in walking, both biologically and with this prosthesis, the trailing leg joint applies very high mechanical powers just at the right time, which tends to affect the center of mass lifting it, and that reduces stress on the leading leg. A common secondary condition in persons with leg amputation is knee osteoarthritis. In persons of age, 50% of individuals with leg loss suffer from knee osteoarthritis, and the normal non-amputee incidence is only 20%. And it's believed by some clinician that it has a biomechanical mechanism or cause. With a bionic limb that emulates lost muscle function, one can, in principle, have a restored calf muscle, restored power plant inflection, and have a knee external aided action moment that's normalized. So instead of having an aging calf muscle, if the person is missing a limb, you can update their robotics so they always have a normal calf muscle function. And I think in principle, we can greatly mitigate the incidence of osteoarthritis. It is commonplace when we fit this device to patients, if the patient has discomfort in their knee, in their hip, in their socket, in their back, it is common that within hours and days that their testimony is that their pain is reduced and sometimes eliminated. This is an example.
On the hill without, killing myself, or feeling my pain in my hip or back or the knee, comes back on my advanced by a third. My pain meds I'm talking about.
So again, I think if we were to race out 20 years and we would ask what's the dominant clinical legacy of powered leg prostheses, it would be the reduction in musculoskeletal stress and the collapse or mitigation of joint disease such as osteoarthritis, which is very, very exciting. All that I've said thus far is about level ground walking. I didn't say anything about going up and down hills, but if you can emulate lost muscle function, obviously you can go up and down hills and steps in a better, more natural way compared to a prosthesis that doesn't emulate lost muscle function. This is a soldier, Steve Martin, the comedian, that lost both of his legs from an IED blast in Afghanistan, now able to run uphill with the emulation of muscle function. A limitation of the current device is that only one joint is actuated, the ankle joint. So we've now built a 2 degree of freedom foot ankle device, where we now have an actuated subtalar joint. This is exciting because the devices that I'm wearing now are only 1 degree of freedom, only actuated ankle. And my balance is clearly pathological. I can do that for about 15 seconds, where you folks in the audience with normal biological limbs could do that all day long. But with a subtalar joint, we can correct for such a balanced pathology, which is very exciting. We're of course building powered knees and linking them to the powered ankles. Transfemorally, it seems to be far more difficult to normalize gait than transtibally, which is a great challenge for the community. Can we normalize metabolism, speed, or stress in a person with an above-knee amputation? That's something we're looking at closely. I'll finish up dynamic interface with a set of ideas that I think are important for the field. So there's a tremendous opportunity in dynamic interface by combining, again, these 3 areas. One is, if the field has what I call a physical simulator, a device with off-board actuation, power supply, and computation with cable drives to the biological joints, where one minimizes the mass that's attached to the human. And in that device, you can put a living, breathing human on an instrumented treadmill in a Vicon motion capture environment. And you can quickly program up an idea for a prosthesis or an exoskeleton, control or sensing paradigm. And one can then test that idea very quickly and see if the idea bears fruit. So imagine it's 3 a.m. and you think of a great idea, and you can, with this device, come in, program it up, and test your idea in a matter of weeks. In today's world, often people build an autonomous device, which takes years and millions of dollars, and then they find out their idea doesn't work, which has happened to me many, many times. So if we combine a physical simulator gait modeling, such as the Geyer-Her model, it's highly adaptive to train, and also human-in-the-loop optimization. So you put a real living human in, you put biophysical control paradigms, and then you can actually feed back all kinds of signals. Everything we can measure in gate labs, you could feed back into the control system, including the neural signal from the human, putting the human in the loop and attaching to the massive computer called the human brain to help us find these needles in the haystack of what works in human-machine interaction. This is one of our first investigations with the simulators. The simulator is being used here at the knee. So we're studying what's the impact of an artificial gastrocnemius. So what I'm wearing now, again, is only soleus tibialis anterior synthetic function. What would be the impact for my body or any body with a transtibial amputation if we were to put an artificial gastroc on the person? So we're applying torques at the knee and the ankle consistent with a linear gastrocnemius force and actually answering this question for the first time. So again, such a simulator is really important for the field. I'll transition now to the electrical interface. How can we signal from the peripheral nervous system, efferent to the device, and then afferent from the device back into the nervous system? So again, the opportunity here that I'll emphasize today in my talk is about 3 areas that I think are important to expand and to merge together. One area is peripheral reconstructive and regenerative medicine. We have to change the paradigm of how limbs are amputated. It's absolutely ridiculous that we're largely amputating limbs in the same way that we were amputating limbs 100 years ago, 200 years ago, etc. We really have better surgeons now and better techniques. It's time we look at this problem again. And regenerative medicine, we can grow nerves to muscle and skin and organs, for example. The second area is optogenetics, which offers, I think, an exciting way to artificially actuate muscle. And the third is muscle sensing and control. So I'll start with surgical manipulations for the case of transtibial amputation. My legs were amputated 35 years ago. God, I'm getting old. And my legs are amputated, unfortunately, in the standard paradigm, where both my calf muscles and my anterior muscles were stitched down asymmetrically. I feel my feet as a phantom awareness, but when I try to move my phantom foot ankle, it feels like my foot's in a ski boot, that I'm being restricted, I can't move it. That's because my muscles were stitched down asymmetrically. What we're doing surgically, and sorry I don't have a pointer, is we're creating a biological pulley, and we're actually mechanically attaching anterior and posterior muscles, such that when a muscle A contracts, it stretches muscle B and vice versa, and with spindle organs and Golgi tendon organs intact, the person, we feel, will get feedback to the spinal cord. Transtibially, you can link several muscle pairs to control ankle, subtalar joint, metatarsal phalangeal joint. And we feel that by doing this, again, when the person moves their phantom foot ankle, they'll actually feel normal joint dynamics. So let me take you through the opportunity here. So again, we mechanically link agonist-antagonist pairs. When one muscle contracts, the other is stretched, and vice versa. If there's no load on the prosthesis, that would give you a nice mapping between prosthetic state and the proprioceptive state that the human is experiencing. When a load is applied, then there's a mismatch. What one can do in principle is stimulate muscle A, in this case the anterior muscle, to vary the load on muscle B. In principle, you could measure the force on the prosthesis with a torque and have that go into a chip that computes optimal muscle artificial stimulation to modulate the force on its muscle partner so that the human actually feels the force via Golgi tendon organs. That's an example of native muscles. One can also play this game with a transected nerve, where surgically you bring together muscles that you either take from the limb that's being amputated away, or you hack from another part of the body. You mechanically link them in a surgical sense, and you put it in close proximity to the nerve supply of interest. So if I want to, if this is a bionic hand, and I want to control my bionic wrist, in my transhumeral stump, the nerves that innervated my wrist flexors and extensors, I would put next to an agonist-antagonist surgically created pair. And when I think and I move my phantom wrist, those small muscle organs would cycle back and forth, okay, after the regenerative process has taken place. So this can apply to both native muscles as also to more distal degrees of freedom that one wishes to control via surgically creative pairs. So we now changed how limbs are amputated. We created these agonist-antagonist muscle pairs. How do we actuate them? Again, we'd like to do actual feedback from the prosthesis into the human, so we want to do force control, position control on those muscle constructs. So we need a good way to actuate muscle artificially. We're exploring optogenetics. So this is an experiment where we inject a virus into the leg of a mouse, and we get expression of a light-sensitive protein in the tibial and peroneal nerves. This is a first demonstration of a transdermal muscle activation. So there's nothing inside this animal. There's no device, there's no nerve cuff. We're simply shining light on the animal's skin. We shaved away the hair so that we get adequate light penetration to the nerve. The animal is under general anesthesia. So by dramatically increasing the amount of protein expression in the nerves that supply this agonist-antagonist pair that actuates the ankle, we get very nice optical control. Many of you know that this may be superior to electrical stimulation muscle because there's evidence that through optical stimulation, the muscle is recruited in a natural way, where as you turn up stimulus, you go from small motor and then large motor units, as opposed to electrically, as you turn up stimulus, you first recruit large motor units. So you go from low force to a force that's too high. So we now want to close the loop on this optical signal. And we're doing that by putting crystals in the muscle. Sonomachrometry, this has been done in the realm of biomechanics for decades. So you have a crystal pair that you put into muscle. You pulse one crystal, there's a sound wave that's sent down the muscle and vibrates its partner crystal. If you know the speed of sound in muscle, and you know a clock, you now can measure muscle length and muscle speed. So we're getting that to measure state, and then using a standard electrode to measure electromyography. With a muscle model, with inputs of muscle length, speed, and electromyography, then one can derive a force. So this just shows crystal data from an animal experiment. So again, we're now closing the loop between the optical signal and these sensors in the muscle. This is just the control diagram. I showed you a control diagram earlier. In the devices I'm wearing that are not neurally controlled, we actually program the microprocessors to run the reflex loops of the spinal cord. With sufficient afferent feedback, we feel that can be relaxed. So if you give enough feedback to the human will have enough information, we hypothesize, to modulate their own neural signal and directly control the motors of the prosthesis. So we're pursuing two projects. We recently performed our first human surgery, amputation surgery, transtibial, where we linked two muscle pairs, one for ankle and one for subtalar joint, through biological pulleys. The human patient reports that they feel normal ankle and subtalar dynamics, And when we image, we actually see the muscles contracting and being stretched in agonist-antagonist pairs. As a first step, we're going to implant IMEs, implantable myoelectric sensors, 4, 1 in each muscle body, and directly do a neural efferent control of a 2-dot foot ankle and explore balance augmentation, for example. We're also working with Dr. Brainmark of Sweden in the realm of osseointegration, not only as a mechanical attachment, but also as a neural conduit. And next year we're going to be doing 2 planned transfemoral amputations, where again we surgically build up these agonist-antagonist muscle bodies and stitch them to the fascia. Each pair is to be used to control 1 degree of freedom. So in this transfemoral system, we'll have a powered knee, ankle, subtalar joint, and metatarsal phalangoid joint. 4 degrees of freedom with cutaneous and proprioceptive feedback. I'm going to finish up with something fun. This is Victoria Modesta. She was born with a leg that did not work very well, and throughout her tweens and teenage years, she hobbled through school and was made fun of, and she finally got fed up and begged doctors to just amputate the limb so that she could have a prosthesis and have a more normal life. And it took her 5 years, by the way, to convince doctors to amputate her leg. They thought she was crazy for a very long time. The day her leg was amputated, she actually celebrated and had a cocktail. She's now an international pop star. We're working with Victoria to go from her now legs that are artistic and exploring body sculpture as an art form to devices that are comfortable mechanically. She's often in excruciating pain when she performs on the pop stage. Devices that are dynamic in a very interesting kinetic sculpture way, and for which she can neurally control that sculpture. So I'll finish up with Victoria's recent pop video. Some of you may have seen this, it's fantastic. We're now exploring how neural implants will enhance her artistry. Thank you very much. Thank you.
What does sweat?
Sweat.
Yes.
It's very important. So if I were to leave this auditorium and go running for a mile or 2 and come back, I could fill your entire coffee glass with sweat. So it's indeed a problem because sweat somewhat acts like a lubricant.
I guess my counter to that is, are there opportunities to design?
Yes, my goal is to first understand what a process is doing. Now it's like chicken sexing. They do this magic and they produce a socket. And they really can't tell you what they're doing. Some people are good at it, some people are not so good at it. So I first want to understand that. But you're absolutely right. Once we fundamentally understand what is comfort, we think it's minimization of soft tissue strain that often occurs at the soft tissue bone boundary. Once we understand that, then we can put forth ways to absorb sweat, ways for the synthetic skin perhaps to push fluids out to its outer surface. Volume compensation, all these types of active systems that we see.
There's one over there, back first. Just want to speak. Oh.
How realistic is the hill model for the muscle?
How realistic is the hill model for muscle? Within certain regions of dynamics, it provides a reasonable estimate. And it's often used because computationally it's very attractive. And we've found that it's adequately descriptive for our purposes. So we're at the case now where we're at the research point now that we can model a biological limb, and then we can use the model parameters, both morphologically and the gains of the reflex moves. Those exact parameters we found in the mathematical model and apply them directly to the controller, and the human walks, and there's no need to modify the gains. So that tells us that we're really making good predictions of where we should be dynamically.
Let's see. So you mentioned the idea of okay. Yes, got it. Okay. So you mentioned the idea of tying the muscles, the agonist and antagonist muscles together for purposes of offering some proprioceptive feedback, which I think is good. But so the question is, to what extent might that have use also as an actuation control input? And in particular, it seems like you could use sonography or implant a magnet and use Hall effect to track the...
So what you're asking, what are the advantages in efferent control?
Is there potential for efferent control?
Yeah, I just neglected to mention that. So the dominant story is actually advantage in the efferent. So that we all know that the minimum motor unit in nature and biology is not a single muscle, but at least two muscles. So that agonist-antagonist pair allows one to control both position and impedance. So if we sense state and force in each of those muscle pairs, we can look at how much the human's co-contracting those pairs or not co-contracting, and get a sense of equilibria as well as joint impedance. So it's also a very powerful model for efferent control. And then you get the afferent as well.
There's one question back there. I think Tobias just
First of all, thank you for your nice and inspiring talk. You point to some directions, so I didn't see could be a potential direction. I want to hear some view from you. So currently, implant prosthetic and the prosthetic we put outside with the socket. Do you think what would be the barrier for us to, for example, connecting the prosthesis you made to the bone of the amputee?
So osseointegration.
Yeah. What's the barrier?
So Dr. Bramark just got FDA approval in the United States for the transfemoral case, but he got it within a certain population of patients. Patients that receive their amputation because of trauma or cancer. So the patients that, for example, lost their limb due to diabetes and circulatory issues, it was deemed that osseointegration is not appropriate. So I think at least for some time, we will have both in the world of prostheses, both invasive osseo-implant as well as non-invasive sockets. So I think as a researcher, we need to pursue both and optimize both.
Yeah, well, what do you see that is currently the barrier for putting such a device connected to
Osseo-implant?
Yeah.
Gosh, it's gaining such steam. And Bramark has done hundreds of surgeries worldwide. And now there's many other surgeons pursuing it in their practice. Everyone mentions infection, but the stats on average, a patient with an osseo-implant has one infection per year. And it's treated locally and goes away in a very short amount of time. Dr. Bramark says it's as common and as non-life-threatening as getting a cold. So yes, that should be solved and will be solved, but the osteo procedure is, I feel, adequate today to move forward aggressively in the clinical realm.
Thank you. We'll take one last question there, just behind you. If you can pass the microphone back, please. Sorry, it was behind you. Never mind.
I think that relates first.
Hello, my name is Nicholas.
Don't fight over the mic.
I come from Sweden, and I'm very intrigued and looking into how can we bring new innovations, like the ones you are working with, which are beautiful. How can we get them into the patients? What movements do you see that we actually make them reach out so they can do the help that we want them to do? What do you see that we are doing today, and how would you actually think that we should go about this?
So are you talking about the bench to bedside translational process?
Actually, even
yeah, I would.
further.
I have a lot of scar tissue. I was talking to Michael Goldthorpe at dinner last night, and all my various scar tissue over the years. So, the dominant impedance to innovation in prostheses is nothing to do with science or technology. It has to do with reimbursement. And it's an absolute threat to innovation. What's happening is great technology is being developed in laboratories within universities or companies, and then insurance and the Centers for Medicare and Medicaid Services, for example, refuse to recognize the technology. And then it's the only way to get the technology is for someone to purchase it themselves, which these devices are expensive and it's out of the reach of most of the population. And, you know, what the end issue is that great technology ends up in the closet not being used. So we have to figure out the reimbursement.
I'd actually like to just bring up one other thing. I see a lot of good settlements at MIT, at Sweden where I come from, like throughout Europe, where we have these innovation hubs where we help new innovations to get going. But what I'm not seeing actually anywhere, and I would like to know if you're doing it at MIT or somewhere else, building the support system around these devices so they actually reach out. Because we can continue to develop technology as much as we want. If we don't have the system to make it reach out, it's not going to get there. And I don't see that the money goes into these kind of efforts. Is that your opinion too, or do we not share it?
Yeah, you're asking very complex questions. So, if the market potential is tiny, the truth is there's going to be tiny investment to support it. So you're only going to get substantial investment if it's a massive argument. So as designers, we need to pick our battles, choose our battles wisely. And back to reimbursement, what we can do as designers is attempt to improve the quality of care with new invention that does not break the bank. Maybe we can improve quality of life at the same price point and perhaps even lower price point. And maybe the gizmo is already described in the Medicare and Medicaid code descriptions. So that's kind of the sweet spot. The devices I'm wearing, just stats, we've raised and spent $60 million. We fit 1,500 people in the world. We currently have 14% of the US market. CMS has not recognized the technology, so private insurance do not recognize the technology, and it's really frustrating. I'll get off my soapbox. Thank you.
Very sorry.